Good morning friends. We, the student of Sri Shivaji Science College, have made a presentation of chemistry on the topic pyrrole, a heterocyclic aromatic compound. Pyrrole is a 5-membered heterocyclic compound. It is a colorless volatile liquid that darkens readily upon the exposure to air. So, to study the pyrrole, let's see the content. In this, we'll discuss the introduction of pyrrole, then the structure of pyrrole, then how pyrrole is synthesized. The next is our molecular orbital structure of pyrrole, then resonance of pyrrole. Then we will study the basic and acidic character, that is the basicity and acidity of pyrrole. As pyrrole is aromatic, so it undergoes electrophilic substitution reaction. So for that we will see the orientation of electrophilic substitution reactions, then we'll see the electrophilic substitution reaction. Okay, so let's start with the introduction. As our topic is pyrrole, a heterocyclic aromatic compound. Firstly, we should know what is the heterocyclic compound. The organic compound obtained by replacing one or more carbon atom of the ring by heteroatoms like nitrogen, oxygen and sulfur are called as the heterocyclic compound. As this is an cyclic compound, hence it is called as heterocyclic aromatic compound. It is important one that it is important heterocyclic compound. It plays a very vital role in the chemistry of living organism. That in many natural occurring compounds like chlorophyll, alkaloids, hemoglobin, etc. are having the pyrrole nucleus in it. It occurs in coal tar and bone oil. So this is the introduction. Now let's move towards the structure. The molecular formula of pyrrole is C4H4NH, or can write C4H5N. Both are the correct one. Then pyrrole is a 5-membered heterocyclic compound. As there are also some 6 members, 7 members and some condensed form, but it is the 5-membered in which 4 carbon atoms are there and 1 nitrogen atom is there. This nitrogen atom acts as a heteroatom. It is a 6 pi electron aromatic compound bearing 1 heteroatom, that we know it's nitrogen. Here we have double bonds, so we have 4 pi electrons there in that 2 bonds and 1 lone pair on the nitrogen. The IUPAC name of pyrrole is azacyclopenta 2,4-diene. So this is the structure. Now then we will see how pyrrole is synthesized. There are many ways to synthesize pyrrole, but here we will see 3 important one, that is from acetylene, from succinimide, from furan. Then from acetylene we will see how pyrrole is obtained. In this, 2 molecules of acetylene reacts with the ammonia molecule and pass to the red hot tube. There takes place the fusion and they cyclize to give the pyrrole molecule. So from this the pyrrole is obtained. The next one is from succinimide. From this the pyrrole is obtained by the distillation of succinimide over the zinc dust. In this, firstly succinimide undergoes the enolization and forms the enol form of it, which further undergoes zinc reduction and gives the pyrrole molecule. So this was from succinimide. The last one is from furan. Furan is another heterocyclic compound in which oxygen is the heteroatom. This furan will react with ammonia and in the presence of hot alumina at the temperature of 480 degree to 490 degree Celsius, they will get react and forms the pyrrole, and the water act as there as a side product. Now we will see the molecular orbital structure of pyrrole. In this we will see the molecular formula, then electronic configuration, then we will see formation of a sigma bond, then formation of pi bond, and lastly is the representation. We know the molecular formula of pyrrole is C4H4NH and C4H5N. Here it is having 4 carbon atom, 5 hydrogen atom and 1 nitrogen atom. There is we'll see now. Next will be the electronic configuration. Now let's see one by one the electronic configuration. First is the carbon. The electronic configuration of carbon at ground state is 2s2, 2px1, 2py1, 2pz0. Then in the excited state it becomes 2s1, 2px1, 2py1 and 2pz1. It forms the 3sp2 hybrid orbital. This 2pz1 orbital is unhybridized and to form the pi bond due to the lateral overlapping. Then electronic configuration of nitrogen in the ground state is 2s2, 2px1, 2py1, 2pz1. But in the excited state it becomes 2s1, 2px1, 2py1 and 2pz2 and forms the 3sp2 hybrid orbital. The 2pz2 orbital is unhybridized, which contains 2 electrons, that is the lone pair electron, and involved in pi bond formation. The last electronic configuration is of hydrogen, that is simply 1s1. Now according to the molecular orbital theory, in pyrrole or the carbon and nitrogen undergoes the sp2 hybridization, and all ring atom in pyrrole, that's the 4 carbon and 1 nitrogen, contains the 3 sp2 hybrid orbitals. The pyrrole ring is planar due to the sp2 hybridization. So this is the electronic configuration and molecular. Now let's see the formation of sigma bond in molecular orbital diagram. It contains total 10 sigma bond, which contain 3 carbon-carbon single bond, 2 carbon-nitrogen bond, 4 carbon-hydrogen bond and 1 nitrogen-hydrogen bond. In pyrrole, all carbon and nitrogen atom contain sp2 hybrid orbital which are half-filled. Therefore, 3 carbon-carbon by sp2-sp2 overlap, 2 carbon-nitrogen by sp2-sp2 overlap, 4 carbon-hydrogen by sp2s overlap and 1 nitrogen and hydrogen by sp2s overlap. In this way, sigma bond are formed. Total 10 sigma bond are formed which lie in one plane and are at 120 angle from each other. Then in formation of pi bond, carbon has one unhybridized p orbital which contains single electron, and nitrogen has p orbital unhybridized which contain lone pair. These are all p orbital are perpendicular to plane of sigma bond are parallel to each other. So lateral overlapping to their s and p orbital give rise to the formation of delocalized pi molecular orbital above and below the plane of ring. Pi molecular contains 6 electrons. Due to this, pyrrole shows aromatic character by satisfying Haeckel's rule, that is 4n plus 2. Therefore, it contains aromatic suggest which opposes addition reaction and favors electrophilic substitution reaction. And its representation is, it is a ring simply pentagon which circle inside, and circle represent pi molecular orbital. Then the resonance of pyrrole. According to the resonance theory, pyrrole is a resonance hybrid which gives 5 resonating structures. The nitrogen atom of pyrrole donates, or we can say its lone pair is involved in resonance, which makes the pyrrole aromatic in nature, and the negative charge is delocalized in the ring, and this makes the pyrrole ring favorable for electrophilic substitution reaction. We will see the basicity and acidity of pyrrole. In basicity of pyrrole, it is acts as a weak base. When pyrrole is reacted with dilute HCl in absence of O2 to form a crystalline salt, which indicate pyrrole is a weak base. Lone pair of electron present on nitrogen atom of pyrrole is available for donation, so it is a basic in nature.
but the lone pair of electron on nitrogen is involved in resonance, so its availability for donation is very much decreases, so it is weak base. It also shows 5 resonating structures. If proton is added to nitrogen by reaction with acid, then the resulting aromaticity, so pyrrole cation, is very unstable. In acidity of pyrrole, it also acts as a weak base, weak acid. When it reacts with solid KOH to form salt called potasiopyrrole, so it is acidic in nature. It also reacts with Grignard reagent to form hydrocarbons. It is weak acid as nitrogen and hydrogen bond in pyrrole is weak bond as the lone pair is involved in resonance. Nitrogen has a positive charge and it abstracts electron from hydrogen and is more stabilized than pyrrole by delocalization of negative charge over the ring, and it shows 5 resonating structures.
Then we will see the orientation of electrophilic substitution reaction. As pyrrole is aromatic in nature, hence it undergo electrophilic substitution reaction. As we all know electrophilic substitution reaction, pyrrole is very reactive towards the electrophile because the pi electron density of carbon is high due to resonance. The electrophilic substitution of pyrrole occurs at position number 2 and position number 3 preferentially. Now we will see the attack at position number 2. This is the C2 position and this E positive is electrophile here. This electrophile will attack at position number 2. That's why the bond shifted towards the C2 position and forming the positive charge at carbon number 3. Again, this bond is shifted towards C4 carbon atom and the positive charge is delocalized on the C5 carbon atom. Then the lone pair of nitrogen is shifted towards the C5 carbon atom as it is electron deficient. Then this forms the positive charge on nitrogen atom itself. In this, the positive charge is delocalized over the ring. Then the hydrogen, that is the H positive proton, on deprotonation gives 2 substituted pyrrole structure. Now we will see the attack at position number 3. Again here E positive is electrophile which attack at C3 carbon atom, due to which it forms positive charge on C2 position and the bond is shifted toward the C3 position. Now the lone pair of nitrogen atom is shifted towards the C2 position and the nitrogen forms positive charge, and then the hydrogen, that is the H positive proton, on deprotonation gives the 3 substituted pyrrole structure. So in case of attack at position number C2 and C3, we will give C2 on C2 position we will give 3 resonating structure, and the C3 position we give 2 resonating structure, so that the 2 electrophilic attack, which is more stable due to more number of resonating structure and greater delocalization of positive charge, then the 3 electrophilic attack we get 2 resonating structure. As pyrrole is aromatic, so it is more reactive towards electrophilic substitution reaction. Here now we will see the electrophilic substitution reaction, that is the nitration and sulfonation, halogenation, and halogenation include chlorination, bromination and iodination, and lastly the Friedel-Crafts acylation. We will see in one by one manner. First, on the left side there is the nitration and on the right side there is the sulfonation. In the nitration, the pyrrole is reacted or treated with cold solution of nitric acid, that is the HNO3, in acetic anhydride at about 0 to 5 degrees Celsius or 283 Kelvin to form the 2-nitropyrrole. And on the right side there is the sulfonation. Here the pyrrole is treated with sulfur trioxide in pyridine at about 90 to 100 degrees Celsius to form 2-pyrrole sulfonic acid. Then we will go to the next reaction, that is the halogenation reaction, which includes chlorination, bromination and iodination. First we will see the chlorination reaction. When pyrrole is reacted or treated with sulfuric chloride in presence of ether at 273 Kelvin or 0 degree Celsius gives 2345 tetra chloropyrrole. Then next is the bromination. The pyrrole is reacted with 4 molecules of bromine in presence of ethanol at 0 degree Celsius or 273 Kelvin to form 2345 tetrabromopyrrole. And lastly the iodination reaction. In this, pyrrole is reacted or treated with 4 molecules of iodine in presence of aqueous Ki, that is the potassium iodide, to form 2345 tetraiodopyrrole. Then lastly the Pyrrole acylation reaction. In this, pyrrole is reacted or heated with acetic anhydride at 250 degrees Celsius or 523 Kelvin. Pyrrole undergoes acylation to form 2-acetyl pyrrole. Here there is no need of catalyst to proceed the reactions, so that this is the Pyrrole acylation.
Now lastly, thank you all of you for watching our video. This video was made by the students of BSc third year bio group. The students are Amruta Chafle, Prajakta Badarkhe and Priyanka Dikshit. This video was made and this whole activity is made under the guidance of PR Padore sir. So thank you for watching our video.